doesn't really change with training, but that's because at rest there's not a need for an increase in VO2 max. There's probably actually a reduction in the need for VO2 max because there's well, we don't need to get into that. It just remains unchanged. Actually, the submaximal VO2 max can slightly decrease with training. And again, that has to do with the combination of stroke volume and the need and the efficiency of the muscle fibers to extract oxygen. Again, right now, maximal VO2 max seems to be the best indicator of cardiovascular fitness. It can increase substantially through training, up towards 15 to 20% of an increase, and that could be because of an increase in, I guess we've already said before, cardiac output and capillary density. Figure 11.1, you could take a look at that. It just shows, like at the bottom, the brain is going to receive us. Let me just. The brain cardiovascular is going to send a signal. It's going to increase sympathetic nervous system activity, which is going to increase norepinephrine, which is going to increase the calcium, which is going to increase contractility, which is going to increase stroke volume, which is going to increase cardiac output, which is going to increase VO2 max. Follow all those boxes up. All right, so in terms of long-term improvement, VO2 max peaks out usually after about 12 to 18 months of training, and after that there's increases in sport performance, but potentially due to increases in oxidative enzymes and such. So after 12 to 18 months, improved in performance are more metabolic than cardiovascular. These individual responses are dictated by how well trained the athlete is, and also hereditary. For each individual, it appears as though that there's a genetically determined VO2 max range that that the individual is somewhat bound to, and that could have to do with lung volume, lung size, the percentage of type 1, type 2 muscle fiber types, the number of mitochondria, and all sorts of different factors. So genetics is a huge determiner in the ability and the amplitude at which a VO2 max can increase. We're right now on slide 34. Training status and pre-trained VO2 max are going to increase their VO2 max gains more than the fit individual. There's just going to be an effect size. So if you're doing a study and you want to see improvements in VO2 max, it might behoove you to work with sedentary and untrained individuals, and you'll see a greater manipulation of VO2 max given the experimental protocol. And again, slide 34 suggests that hereditary is the main driver of variance in VO2 max, accounting for 25 to 50% of the variation. Figure 11.3 shows a correlational chart between twins. It shows in blue identical twins, in red it shows fraternal twins, and in green it shows non-twin brothers. And the clustering around the mean for monozygotic twins in the comparison between VO2 max is closer to 1, and that signifies that the identical twins have VO2 max values that are more correlated than the other two groups, which means that because the identical twins have the same genetics, it appears though that genetics is a main driver in VO2 max. Males and females are going to have different values of VO2 max, particularly because of the body size difference. And because of the high genetic component and the gender component, it appears as though some individuals may respond to the aerobic training differently than others. There could be high and low responders. So we have to be aware of the fact that some of this training may affect individuals' VO2 max, heart rate, blood pressure, and all those things differently than other people. Right now we're on slide 39. Endurance training is critical for endurance-based events. It might not necessarily be um, uh, either 100% necessary for every single sport, though. And the type of endurance training is dependent upon the sport as well. For instance, in gymnastics, the long duration, low intensity aerobic slow glycolysis is not really as important as training the anaerobic endurance, the ability for my athletes to utilize fast glycolysis and to go through that pyruvate lactic acid and then neutralization of lactic acid and resynthesis of ATP is potentially more necessary for gymnasts than it is for long-term endurance, so long duration endurance swimmers. For anaerobic endurance training, there is somewhat difficult to measure anaerobic power and capacity. The Wingate test, which is a 30-second all-out bike sprint, is utilized to measure anaerobic power. But because VO2 max isn't the number one criteria any longer, it's somewhat difficult to measure anaerobic power. Adaptations in muscle due to anaerobic endurance training could be that there's an increase in type 2A and type 2X cross-sectional muscle fiber area. There's an increase in type 1 cross-sectional fiber area, but because it's anaerobic training, there's a lesser extent of type 1 muscle hypertrophy. And there could be a case that there's a reduction in the percent of type 1 muscle fibers and an increase in type 2 muscle fiber types, either through transitioning from one muscle fiber type to the next or through hyperplasia, but still more research is necessary. In regards to anaerobic training and increases in the ATP-PC system, for the most part, there's an increase in strength, and the increase in strength is going to potentially be the number one driver of improved sport performance with anaerobic training in regards to the ATPP system. But rather in the fast glycolysis system, there is an increase in many different enzymes that are going to allow for the breakdown of sugars in the absence of oxygen, like phosphorylase and phosphofructokinase and hexokinase. But again, most performance gains are potentially from increases in strength. It shows here that there's a citrate kinase, a succinate kinase, a citrate kinase, and other oxidative enzymes or enzymes that are necessary in fast glycolysis. And you'll see with training, there's an increase in both of those enzymes with training. So it could be the case that the increase in enzymatic activity allows for a greater oxidation, not oxidation, a greater rate of breakdown from glucose to pyruvate and then to lactic acid. All right, slide 44 talks about high intensity interval training, and appears as though that high intensity interval training is going to have very similar cardiovascular fitness effects as long-term endurance training. And because high intensity interval training takes much less time, maybe it's a more efficient way to allow for these cardiovascular changes to occur. If an individual is interested in doing high intensity interval training, what they would do is run that way for 30 seconds, rest for 3 minutes, run that way for 30 seconds, rest for 3 minutes. Do that 8 to 10 times. It should take about 21 minutes to get a good bout of high intensity interval training and positively impact your cardiovascular system. It shows during high intensity interval training maximum cytochrome oxidase activity and also cycling performance. And with endurance training, high intensity interval training, you can see that there is an increase in the maximal cytochrome oxidase activity and also an increase in cycling performance, shown by a reduction in time. In regards to cross training, it's another method that utilizes multiple sports at once to try to increase the metabolic capacity of all of the metabolic pathways all at once. So it's utilizing resistance training, endurance training, both aerobic and anaerobic endurance training, so that uh, gains across multiple systems are possible. And then there's a table on 11.5 that summarizes some of the major changes across the aerobic and anaerobic enzymes that occur because of training. So, a good amount of the aerobic and anaerobic endurance training and sport performance increases are due to changes in oxidative enzymes. Um, so, we want to keep that in mind. And then, slide 49, there's a video where Stephen Piazza discusses what makes a good sprinter. And that's the end of chapter 11. Hope to have a good day. Take care.